In this video, we're going to discuss Greens theorem, which is one of the culminating theorems of multivariable calculus. So to be able to state Greens theorem, we need to sort of set up a particular situation. So that's where we're going to begin. So we're going to start by letting C be a simple closed curve and we want the curve to be in the plane, and we want it to have positive orientation, and we want it to be given by a vector function, r of t, where t ranges from a to b. Now, there are a few words here that describe this curve C, some of which we've not used before. So the curve C has to be simple, it has to be closed, and it has to have positive orientation. Right? So let's quickly just define what these three terms mean. So simple, in the context that we're talking, simply means the curve doesn't intersect itself. So for example, we would not have a curve that's shaped like a figure 8 because the figure 8 would cross itself in that middle point in the middle of the curve. A closed we have used before, but just to be complete, we'll indicate that definition again. And a closed curve just means it has the same initial and terminal points. So the curve starts at the same point and it ends at the same point. And then since it's simple, that is the only point in which will lie on the curve twice, but no point in the middle of the region or of the curve will intersect itself. And the other term here is positive orientation. And this just means that the curve is going to be oriented counterclockwise. And the region is always on the left of the curve. So with any type of simple closed curve, you'll always be able to traverse it in a counterclockwise direction so that that region is always on the left side of the curve. We can then give that region a name, so let's call it D. So let's let D be the region bounded by the curve, so the region inside the closed simple curve. And the last thing we need with Greens theorem, not only do we need a curve, which has all of these properties in this region D, we also need a vector field. So let's just let F, which we'll look at as scalar functions or scalar fields P and Q. So F will be Pi plus Qj. This is just going to be a vector field. Right, so these are the ingredients that we need for Greens theorem. A simple, closed, positively oriented curve C, the region D bounded by that curve, and a vector field F. And so a picture of the kind of thing that we might want. So I want a closed curve, a closed simple curve. So I'm going to go do anything here. I can kind of make this do anything I want as long as it doesn't come back and cross over itself. Right, so here is a closed simple curve. We have a direction. We want it to be positively oriented, which means we want it to go counterclockwise. So I'll just draw some arrows along the curve indicating the direction that the curve is traveling. And the region inside the curve is what we are denoting D. So this region all in here is our region D. Now looking back at our study of multivariable calculus so far, we've seen two types of integrals that would apply to this situation. We could compute a line integral over the curve C. Maybe I'll label the curve here. I didn't actually label this. So the black curve there is curve C. We have a curve in the plane, so we could compute a line integral over that curve. And we also have a region in the plane, a nice open region there in D, the area inside the curve C. And we could compute a double integral over that region. And Greens theorem basically tells us that if we compute the line integral over that vector field f that we just picked, and we evaluate the double integral over the region D for a particularly related function to that vector field, that we actually get the same value. Right, so let's give a precise statement of Greens theorem. Right, so this particular version of Greens theorem will say the following. So we need to let C be a positively oriented simple closed curve in the plane and D is going to be the region bounded by C. So this is exactly what we were just looking at before. So if my scalar functions of my vector field P and Q have continuous partial derivatives, which we've seen is necessary for the different things that we've looked at, so if they have continuous partial derivatives on region D, then the line integral over C of P dx plus Q dy is equal to the double integral over the region D of the function del Q del x minus del P del y. And double integral is is integrated with respect to the area differential. And so this statement here, under the right conditions, where C has these properties, and D and P and Q have these continuous partial derivatives, this says that on the left-hand side, this integral of a vector field, right? So remember, this is also the integral over C of the vector field f dr, where f is equal to pi plus qj. So the left-hand side is the line integral of a vector field, and the right-hand side is just a standard double integral over a region D, which we could use, because of the continuous partial derivatives of P and Q, we are able to use iterated integrals and Fubini's theorem to compute if necessary. So let's take a look at an example. Let's say we wanted to evaluate the following integral. So we want the line integral over C of x to the fourth dx plus xy dy, where C is the triangular shaped curve consisting of 3 line segments from the origin to the point 1, 0, from the point 1, 0 to the point 0, 1. And lastly, from the point 0, 1 to the origin. Right? So we have this line integral of a vector field, x to the fourth dy plus xy dy. And we want to integrate that over a curve, which is the union of 3 line segments. Right? So to put the given pieces here together, notice that we do have p as x to the fourth, and q is xy. Right? So our vector field consists of these two scalar fields. And our region, or rather our curve, if I mark 1 here on each of the axes, our curve is the union of this line segment. So I would maybe call this C1. Then we have from 1, 0 to 0. Well, I'm sorry, 1, 0 to 0, 1. Might call this C2. It goes in that direction. And then 0, 1 down to the origin, this would be C3. Okay? So we could certainly, once we see this, we can certainly just compute this line integral directly as a line integral, but notice that in order to do this, we would have to compute the line integral over 3 line segments. So we would have to find a parameterization for each of these, compute the line integral, that would be 3 line integrals we have to compute, and then add them together. This is certainly not impossible to do, but as we're going to see here shortly, by using Greens theorem to rewrite this as a double integral over this triangular region D, which will be the interior of our triangle. So D is going to be this area in here. We'll be able to do this integral much simpler just using the double integral over this region. Okay? Now the only thing we're going to need, in addition to what's on the screen right now, is we are going to need the equation for the hypotenuse of this right triangle. And of course, this is going to be y equals 1 minus x. So it's going to be a relatively easy line to figure out. And so before we lose the graph and everything, we want to just quickly make sure that Greens theorem does apply. So notice that this curve C, it is a simple curve. It does not intersect itself. It is a closed curve. It both starts and ends at the origin. And it is positively oriented. The arrows I drew in as we went around do go counterclockwise. All right, notice if started at the origin and went up to 1, 0, and then down, or I'm sorry, up to 0, 1, and then over to 1, 0, and then back to the origin, that would be a negatively oriented curve, and so we'd have to do something different other than just apply Greens theorem as is. Right, so we know that Greens theorem applies, so let's apply it. So the integral that we want to compute is the integral over c of x to the fourth dx plus xy dy. Right, and again, this is our function p, this is our function q. And so Greens theorem says I just want to compute the double integral over the interior of my curve, which is that triangular region, of the function del q del x minus del p del y. Okay. So in order to set this double integral up, we want to look at that particular region. And so we're going to use an iterated integral. This is Fubini's theorem since we have continuous partial derivatives. And in this case, I'm going to do an integral that integrates with respect to y first, and then x. Right? And so by looking at that region D, we see that y ranges from the bottom of y equals 0, and it goes up to the curve y equal 1 minus x. Okay. And then x would range from 0 to 1. Okay. So those are our bounds for our integral, the bounds for our region, x going from 0 to 1, and y going from 0 to 1 minus x. And now we look at our integrand function here. We have dq dx. All right, q is xy, so when I differentiate that with respect to x, I just get y. And then I want to subtract del p del y. All right, well, p is x to the fourth. So when I differentiate that with respect to y, we get 0. Right? So I'm literally computing a double integral over the function y. Right? And this is quite easy to do. So we're going to have the integral of 0 to 1. When we integrate the function y, of course, we get y squared over 2. And that's going to range from 0 to 1 minus x. So we end up here with 1/2 1 minus x squared minus 0. If we want, there's a couple ways we could go about this one. We could use a quick substitution, let u be 1 minus x. I'm just going to opt to expand this out, so it's going to be 1 minus 2x plus x squared, right, dx. Right, and so we have 1/2 of x minus x squared plus x cubed over 3, evaluated from 0 to 1. Right, so we're going to have 1/2 times, we have 1 minus 1, which is 0, plus 1/3. And then we subtract 1/2 times 0, which is 0. And so we have a value of 1/6. And so Greens theorem allows us to compute this integral of a vector field as this double integral. The double integral is relatively simple to compute. And we get this value of 1/6. If you want, I'd encourage you to go and try to compute the line integral directly as a line integral. So again, you'd have to compute for each of those 3 sides of the triangle. You'd have to find a parameterization for each. That's not hard to do. And then you'd have to substitute that into the vector field and those quantities and compute that integral. And you'll see it's not terribly difficult, but you do have to compute 3 different line integrals and then add those together. The benefit here is we have to compute one double integral, which ends up being an iterated integral with 2 integrations in this particular instance. But typically these double integrals are a little bit easier to compute than the line integrals that they are equal to. Right, so this is a very standard example of how we typically use Greens theorem in practice. This is where we're going to wrap up this particular video, but the next video is going to consist of just several other examples of using Greens theorem. And so check that out to see a few more examples of this theorem.